described the measurement, even though the theory of weak lensing was developed in the 60s, it took until the first decade of the 21st century for the detection of weak lensing by large-scale structure, and this was made possible by the advent of large format CCD cameras. And so after 40 years, finally the weak lensing signal was detected. And there exists now a large number of measurements. In fact, they're probably not all there. Dating from the year 2000 all the way to today. Okay? And now weak lensing has been detected convincingly from ground-based telescopes, using space-based telescope, HST, the Hubble Space Telescope in this case. It's been detected in the radio, it's been detected via different measurement methods, different telescopes, different techniques, and so on. And so now the field has improved both in precision, statistical precision, and systematic control. So obviously I won't tell you about all these measurements. I'll pick some of the latest ones and show you where things stand with the observations. So first, and maybe it would be good to, somebody could lower the blinds because that we have more contrast. Thank you very much. So first, here is a mass map done with weak lensing. So let's wait a few minutes, you can probably see it better. All right, so this is not a simulation. Thank you. So this is not a simulation, this is a real mass map made with weak lensing. This was done with a Hubble Space Telescope observations. As before, the light blue regions correspond to overdensities, and the dark blue regions correspond to underdensities. And you see a complicated pattern of structures. This is the deepest map that we have. By deepest means where the signal per unit area is the largest. Okay, we now have maps that are much larger in the sky, but they don't have the same sensitivity. So what this, I mean, the sensitivity per unit area on the sky is the highest. And the reason this is the case is because this was done with the Hubble Space Telescope, which is a space telescope which does not have the problem of the atmosphere. And so the resolution of the point spread function is much smaller, which means that one can detect a larger number of galaxies per unit area, which means that the map can have less noise per unit area. Okay? So just to give you an idea, this is about a 2 square degree region. The surface of the moon will be about the full moon will be about like this. So it's still a relatively small region on the sky, but this is still correspond to a very large observing program. The size of the Hubble Space Telescope field of view is only a few arc minutes. So basically, like the Hubble Space Telescope field of view would be about like this, about that big also. So this was done with a very large mosaic of Hubble Space Telescope images. It doesn't look like this now because there's been a lot of processing and all the observations exposures were combined into a single map. But at the time, this was the largest Hubble Space Telescope observing program ever done. Okay, so this is the map that we get. We get basically this pattern. These are clusters of galaxies. Maybe there's some trace of filaments. Okay, and of course, the first thing to do is to check whether how does it look like compared to the visible light, to see whether at least the structures that we see make sense. So here is a comparison between the two. So the white contours correspond to the mass map from before. So basically it's the same thing as the blue map I was showing you before, but instead of showing it with a color scale, it's shown with contours. All right. So the white contours correspond to the weak lensing mass map, and then the different colors correspond to the visible matter. Basically, the blue and the yellow corresponds to starlight, okay, or visible light in the light in the visible, either by counting galaxies or by accounting for the amount of stars available, and the red contours, the red color corresponds to X-ray gas, to X-ray observations, which trace the X-ray gas, which settles at the bottom of gravitational potential and is also another form of the baryons that one finds in clusters or even on large-scale structure. So you see that, roughly speaking, the overdensities corresponds to also to overdensities in the light. So there tends to be light. The visible matter is also concentrated in a lot of the peaks. There's also X-ray gas that is found in some of the deep potential wells, which is a well-known fact. As the baryons collapse into a cluster of galaxy, it gets heated up by during the gravitational collapse, and one can see it in the X-rays through an emission process called thermal Bremsstrahlung. But so there's some correspondence between the visible light and the mass, which mostly trace the dark matter. But you see that the relationship is complicated. And there's a lot of very interesting astrophysics one can do by comparing the distribution of dark matter, that of baryons, and try to study the way structures form and all the baryonic processes that take place. Okay. So as I said, making map or mass mapping is one way of analyzing the weak lensing. So you take you take your images, you measure the shear using the technique, then you take pixels, you measure the average shear inside the pixel, and you make a map. And then in the weak lensing regime, one can inverse the shear map into a mass map, and this is what is done here. But for cosmological application, it's more convenient, or it's more convenient to consider the statistics of the shear field. So then one takes correlation functions and compare to theoretical models of structure formation. And this was done here. It was done several times. This is one of the latest one by Schrebach and collaborators. So this is done using the same data, this Cosmos Hubble Space Telescope weak lensing observations. And what is shown here is the correlation function of the shear. Okay, so this corresponds to the amount, the 2-point function of the shear as a function of angular separation. What is shown here in black, so this is angular separation. You see in this survey one can probe a few arc minutes or sub-arc minutes all the way to a few tens of arc minutes. And then what is shown here is the correlation function, and in black is the E-mode correlation function, and in red is the B-mode correlation function. And if you remember, the weak lensing excites only E-modes. So we expect, if we've done our measurements correctly, and if we corrected for all the systematics, to get 0 B-modes. And you see that that's indeed the case. The B-modes are consistent with 0, while there's a significant E-mode detection. And that's a very strong indication that we detected lensing and were not contaminated by other systematic effects. So what that team did is that they measured the shear field, measured the correlation function, took combination, separated E and B, and checked for the systematics. Here is the prediction for different theoretical models. And one can just fit this model through a Bayesian analysis or other, and then make constraints on cosmological parameters. And this is shown here, so that's what they find. So on the top plot is the constraint on a plane of parameters. So of course it's very hard to plot six-dimensional parameter space. So usually we project it into 2 dimensions. So this is a projection into 2 of the parameters that are considered. This one is omega matter, so the amount of dark matter. This is in a flat universe, so this is also 1 minus omega lambda in this case. And this is sigma 8, so that's an important parameter. So sigma 8 is the amplitude of matter fluctuations smooth on 8 megaparsec scales. Okay? So this represents basically it's a way of quantifying the amplitude of the matter power spectrum. All right, so you take the volume at our cosmological epoch, look at the perturbations, the matter perturbations. You put a sphere of 8 megaparsec, measure the mean density in that sphere, move it to another place, measure the mean density, and so on and so on and so on. Build a histogram, and the sigma 8 is basically, well, sigma 8 square is the variance of that distribution. So it's basically a variance of the matter perturbation smooth on 8 megaparsec. Just a convention. The 8 megaparsec is a convention, a convenient convention to normalize the amplitude of the power spectrum on that scale. Okay? And you see that with the 2-point function measurement that is considered here, there is a degeneracy between sigma 8 and omega matter. Okay? So you see that we can with a 2-point function with only one redshift bin, one can constrain it, but there's a degeneracy between the two. And this is the combination of parameters. So this combination between sigma 8 and omega matter is the combination of parameters that one constrains the best with weak lensing, or that weak lensing is most sensitive to be precise. The reason is that sigma 8 gives us the amplitude of perturbations, matter perturbations at relatively low redshift, and this is what really weak lensing is sensitive to. So weak lensing measures these perturbations. That's what it does. And also it turns out that, of course, omega matter is important, because if omega matter equals 0, then there's no matter to do the lensing. So it turns out it's the combination of sigma 8 and omega matter that are the most sensitive combination of parameters that weak lensing can measure. That's why you will see in all the results, there's always a measurement of this amplitude, sigma 8, on this plane. Okay? And that can be compared with other probes, as I'll discuss a bit later. Okay, with this, it's still a relatively small survey. So it's the largest survey we have from space, at least contiguous and used for weak lens, for cosmic shear. But one can already start putting constraint on other parameters. It's much harder, and for the moment the errors with these survey are still quite large. But for instance, one can try and constrain W, the equation of state parameter for dark energy. This is assuming that W is constant. So this is omega matter versus W. And you see again there's a degeneracy. And there's basically an upper limit on W. And W equal -1, which is a cosmological constant, is consistent with the observations. Okay. So this is with the Cosmos survey. Now, one can also try to make the measurements on the ground, and these are some of the latest measurements from the ground. This is a measurement with the Blanco and Mayall telescope, which are two telescopes run by NOAO, which is an American observatory, with, of course, international participation as well. And what is shown here is a region. So remember, the Cosmos field is 2 square degrees. This is 10 times larger. This is 20 square degrees, but not as deep. So the galaxies that are considered are not as faint. And also, because there's the atmospheric seeing, then the resolution is poor. So we lose. So one loses galaxies when we go on the ground. But the advantage, of course, is that the field of view of ground-based telescope that exists now are larger. And also, accessing time on these telescopes is not as difficult as with the Hubble Space Telescope, which was, of course, in very, very high demand. So one can cover larger areas. So we compensate from having poor resolution by having larger areas. So this is a measurement 20 square degrees down to these magnitudes, which is basically a measure of how faint the galaxies in the survey that can be detected in the survey are. And one gets, and they get these results. You see again the B modes, the E modes. You see that again the B modes are consistent with 0, and the E modes have a very clear detection. This is again the shear correlation function as a function of angular scale. You see also that they can extend to larger angular separation theta, because the survey is larger, so they can access more larger scales, or another way to say, we can more modes, okay, large scale modes, okay. And this is the dashed line, different colors correspond to prediction from the lambda CDM model with different values of sigma 8. So of course, this is a good illustration. As sigma 8 goes down, so it goes from the red, blue, light blue to this, I guess it's green. I don't know what color is this. This is. Then if you reduce sigma 8, and then the amplitude of the expected lensing signals goes down, and vice versa. If sigma 8 goes up, then the amplitude goes up. That's why, because sigma 8 controls the amplitude of perturbations, it also has a direct effect on the lensing amplitude, and that's why lensing is so sensitive to this parameter. And again, they can get constrained on sigma 8 and omega matter. This is the constraint from this. So they call their survey the deep lens survey. Okay, so they get the orange contours, and then one can then combine this measurement with other probes. So this is a combination with the WMAP7 measurement. This is a cosmic microwave background space-based experiment that predated Planck. So at the time, that was what they used. And WMAP was getting the blue contours. And then you can combine them using this Bayesian kind of framework. And then you get the green contours. Okay, so you see, in this case, they agree quite well. And you get something very consistent with omega matter equals 0.3 and sigma 8 a little bit above 0.8, between 0.8 and 0.9. And you see that illustrates the power of combining different cosmological probes, because on their own they may have degeneracies, but combined together they give you, you break some of the degeneracies. Degeneracies is a term for the fact that it's when the constraint in some combination of parameters are linear like this or extended. It means that we cannot, with this, for instance, this probe, weak lensing, we cannot measure sigma 8 and omega matter independently. We can measure only a combination of them into some direction in parameter space. That's what degeneracy means. So not only the probe combination allows us to check systematics, because after all, if there's a systematic in the weak lensing or systematic in the CMB, maybe they would not agree. The contours could be disjoint. But the fact that there's a common area indicates that at least there's no evidence for systematics as far as this plot is concerned. And then we can also combine them and get more precise measurements and break degeneracies. Okay, now going wider. Yep, question.
So how does calculating the posterior from multiple data sets work? Do you just multiply the probability?
Yes, you basically multiply probabilities, or another way to do it if you want to do it early. So either if the two experiments are completely independent, then you can multiply the probabilities. If they're not completely independent, you can also combine it at an earlier stage. And what you do is, instead of considering the likelihood of one, you consider the joint likelihood of both. Okay, and then you run your Monte Carlo Markov chain using, instead of having one likelihood, you have both likelihoods that you multiply.
So then the 1 sigma and 2 sigma that you define,
yes,
would be the result would be based on your result after the multiplication, not just the intersection of the two regions.
Yeah, so it's not intersection. I mean, these are the contours. I think in this case is 68%, 95% confidence levels, corresponding, if it were Gaussian, to 1 sigma and 2 sigma. So in every case, they get the Markov chain gives you a lot of points, and then you count the region where there are 68% of the points, and you draw that contour, and then the region where you have 95% of the counts. After you've done this joint Monte Carlo analysis, basically, by combining the two experiments. Because typically you use the same priors, so you use the same prior, but then you use the likelihood together. As I said, if the experiments are completely independent and the priors don't matter, you can also multiply the posterior, but usually it's better to do it by doing the Monte Carlo with the joint likelihood together. Yeah.
Why are the contours for lensing and CMB orthogonal?
Why are the contours
Orthogonal to each other. That is what.
Yeah. So, I mean, there's no easy explanation, but basically the fact at least that they're not the same or in different directions come from the fact that the weak lensing measures the amplitude of fluctuation. So sigma 8 is the amplitude of fluctuations today. All right. So weak lensing or close to today, and then weak lensing measures that amplitude very close to today. Let's say redshift 0.5 or 1 or whatever. So weak lensing is a measurement of the present day fluctuations, while the CMB, most of the CMB also can measure the amplitude of perturbations, but at redshift of 1,000. Okay, and in order to then turn it into a constraint on sigma 8, you need to basically evolve the structure from redshift of 1,000 to today. So the constraint on sigma 8 from WMAP7 then will depend also on the growth factor. So So because they're measuring the structures at different redshifts, it turns out that the constraint, the degeneracy structure is different. For instance, I don't know if I'll show you this, but even in lensing, if you change, so this survey has a median redshift of 1. So the galaxies have a median redshift of 1. If you change the redshift of the galaxies, these contours rotate a little bit. Okay? So for instance, if you make 3 redshift bins, one of them will be like this, one of them will be like this, one of them will be like this. And in fact, when you combine the different measurements for different redshift bins from weak lensing, you can start breaking the degeneracy that you have with weak lensing if you only have one redshift bin. So some of this is coming from the fact that they are measured at very different redshifts. Most of the probes that measure the amplitude of perturbations at low redshift has a degeneracy like this. That's the reason. That's a good question. Okay, so this is another measurement. So this was going 10 times wider than the Cosmos, and now let's go even 10 times wider, but shallower. So every time we go wider, but shallower. This is a measurement with the Sloan Digital Sky Survey Stripe 82 by Lin et al. See here they have about 300 square degrees, 275 square degrees, so about more than 10 times larger than the previous measurement, but they're shallower. You see the median redshift now is 0.6. While in Cosmos it was larger than 1, previous one was 1, now it's 0.6, so it's shallower and wider. They also have a rather large seeing, so atmospheric seeing is quite large in this survey. Now they can still do the measurement because the galaxies are closer, they tend to be a bit larger. And then here what's interesting is that they did, instead of considering only the correlation function in real space, here they did a measurement of the power spectrum of the lensing, which is one of the first measurement with a good, relatively good signal to noise. So here you see the measurement for the E modes. Okay, just pick one of the colors. This is a different analysis. So let's say the black one. So you see they get the E modes like this. This is a theoretical prediction, or for one value of sigma 8. And then these are the B modes. So just pick one color. Let's say blue or pink. And you see that they're significantly lower. And these symbols means that they oscillate between positive and negative. And then again, they can fit this to a model and constrain parameters. And once again, this is a constraint on the sigma 8 omega m plane. So that's their measurement, the Stripe 82 measurement. Constraint in red and orange. And this is WMAP here. And this is the combined. So in this case, it was a little bit lower than WMAP. Of course, the errors are quite large, still consistent. And then when combined, you get these values. A little bit lower omega m and a little bit lower sigma 8 in that case, as you can see. But the errors are quite big. Okay, and this is the measurement that until recently was the best measurement from weak lensing with the higher statistical significance. And this was a survey called the CFHG lens survey done with the CFHG telescope. This one has 154 square degrees, so a little bit less than the one I just showed you with the Sloan Digital Sky Survey, but deeper, and also with much better image quality, with very good image quality. Okay, with a seeing which is much smaller, because this is done in Hawaii, in one of the best sites that we have in the world, with very good atmospheric conditions. And what you see here are the correlation functions. So this is not E and B. This is just one of the correlation functions. Here we're not showing the E and B decomposition. They've also done it, and also the B modes are small and so on. So this is the correlation function. They also take into account some of the intrinsic alignments and so on. Here, what's interesting is that they divided the survey into different redshift bins. So they divided the galaxy in different redshift bins. And they measured the correlation function in these different redshift bins. And they also looked at the cross-correlation between redshift bins. So they have a large number of correlation functions that they could measure. Both the redshift bin with itself, let's say this is one of the redshift bin correlated with itself, but they can also look at cross-correlations. So these are the redshift bins correlated with themselves. So they have here 6 redshift bins. but they can also look at the first one correlated with the second one, first one with the third one, and so on and so on. So they have a large combination of correlation functions that gives them a lot of tomographic information. And from that, they could also constrain cosmological parameters. So here is their constraint. And what you get again on the omega m sigma 8 plane, this is a constraint from their lensing measurement. This is WMAP 7, okay, the blue, in pretty good agreement. And then the combination is the green. And then if you put in BAOs and other probes, you get even the white contours even smaller. Okay. We'll come back to this. This is the constraint compared to the WMAP 7 experiment. Later I'll show you the comparison with Planck, which is a more recent measurement of the cosmic microwave background and the constraint on their parameters. Okay, and then also they could start constraining the dark energy parameter W, and here is the constraint. So again, this is from WMAP. This is from the CMB alone at the time, WMAP 7, and this is when let's say the pink is what happens when you add the weak lensing plus WMAP 7, and eventually when you add everything, you get the white contour. Okay, many other probes you get the white contour, and you see that it's consistent with -1, with an error of about 20% or so. Okay. So it's consistent with the cosmological constant, but there are still some significant, well, 10–20%, there are 20% errors on uncertainty on this W parameter. So it's consistent with the cosmological constant, but there's still room for other models to also be valid. Okay, so as I said, the Planck surveyor made a more recent measurement of the cosmic microwave background. And so the Planck team also compared their results with they combined their results with many different probes and compared their results with many different probes, and in particular with the weak lensing measurements. So this is a plot from the Planck collaboration, the paper that they released last year, which is their latest analysis of the Planck data. And again, on the sigma 8 omega plane. And this is a compilation of the results. So basically, Planck gives these contours, Planck alone, so the CMB gives these contours here. And the CFHG lens result I was showing you before are the colored points here. Okay, these colored points. Okay, and you see that the Planck results now are a little bit higher than the CFHG lens results. That's because the Planck, compared to WMAP, first has smaller errors, and also have moved up a little bit. So now there starts to be a little tension between the weak lensing measurement and the Planck measurement and the CMB measurement. It's not a very significant tension. If you just look at it on this plane, it's only 2 sigma or so. But actually, if you look at it in multidimensional plane, it's quite a significant. If you include all the parameters, it's quite a significant tension. But at least on this plane, it's only a 2 sigma tension. Now it turns out that actually, and then you can combine with other experiments and get tighter and counter constraint. Now what's interesting is that this Planck result seems to be in tension with other measures of the amplitude of the fluctuations from large-scale structure measurements. So not only from weak lensing, but it turns out also from counting clusters. The clusters constraints tend to be a bit lower than the CMB constraints. And in fact, that's something that we'll talk about a little bit later. You can also do weak lensing with the cosmic microwave background itself. So the cosmic microwave background also gets lensed. And now it's measured very well. In fact, I'll show you the Planck measurement and other measurements in a minute. And that gives another measurement of the weak lensing power spectrum, this time with having the CMB as a source as opposed to having galaxies. And that's what they find for the constraints that they find for the CMB lensing with Planck itself. All right? And you see that it's also a little bit low compared to their primordial fluctuations. Again, the significance is not very high. Okay? It's not very significant, but if anything, all the large-scale structure measurements, at least until recently, tended to be on the low side compared to the Planck measurements. So that's what we call a tension between the probes. And the tension between the probes, if confirmed and significant, which is not quite the case now, but what does it indicate? It indicates that either there's some systematics in one of the measurements or several, okay? Or, if that's not the case, it means that the model is not right. Because all of this depends on the fact that we're assuming lambda CDM. So it means that there might be new physics that one needs to add in the model. You can consider other physics, you can make W change, you can add neutrinos, you can do whatever you want. And then hopefully that could resolve the tension by adding degrees of freedom in the model to allow for the weak lensing to have a lower amplitude than the CMB, for instance. Okay. And of course, a lot of theoretical work has gone into this in propositions for explaining some of this tension. But I think my personal view is that there's still room. First of all, it's not that significant, at least on this plane. And second of all, one should watch for systematics anyway. So let's wait for better measurements of the large-scale structure and further analysis of the Planck data, which are still continuing to be analyzed, especially for the polarization. Okay, and then, so this was the situation until basically early last year or so. And now what's very exciting is that the next generation of weak lensing experiments are now giving their first results. Okay, and there are 3 new generation experiments which has been turned on a few years ago or a year ago. So one is the dark energy survey, the second one is the KIDS survey on the VST, and the third one is the Subaru telescope. Okay, and then these 2 of these, the KIDS and the DES, have published their first results. These are results on a very small fraction of the data they will eventually, fraction of the sky that they will eventually cover. So this is still first results, and certainly does not reach the accuracy that the full surveys will reach. But it's still, but it's already quite interesting. So that's what I'll show you now. So first, the KIDS survey. So this is done with a VST telescope in Chile. This is the first 100 square degrees of the survey, which will eventually cover over 1,000 square degrees. I can't remember the exact number. I think it's 1,500, but I might be wrong. But it's certainly much larger than this. So they observe in 4 bands. Okay, U, G, R, I. These are astronomical conventions for denoting the filters. So it goes from the blue to the red in the visible. It's relatively deep. It has a median redshift of 0.5 after they make all their cuts. And then it has a very good seeing. So the image quality on this site is very good. Sub-arcsecond seeing or less. And so they published their result in this paper by Kuishken et al. Last year. And they showed their first measurement of the correlation function of the shear. And they find, so forget the other colors, so look at the black line, which has all the corrections. So you see the E mode here as a function of scale, and the B mode. So the B mode is consistent with 0. The E mode have a significant detection. You notice that they can go to quite large scales because they have a relatively large survey, 100 square degrees or so. And they find this measurement here. Because it's their first, at least in their first paper, they don't go and get cosmological constraint from their measurement. I suspect it's because it's just the first analysis. They just wanted to demonstrate that the survey is working. And I'm sure that in the next papers, they will start doing maybe new version of the analysis and start getting cosmological constraint from it. But at least it's very encouraging that it's working well. And they have a very nice paper here explaining all the steps in the analysis and the check of systematics, and it's looking very nice. And then there are results from the dark energy survey, which is done with the Blanco telescope at CTIO. You see the Blanco telescope here. It's a 4-meter telescope in Chile. This is a relatively old telescope, but it's been refurbished and improved. What is new is the camera, which is one of the largest astronomical camera in the world. It's not the largest, one of the largest. But combined with the telescope, it makes it the most powerful camera in terms of speed that we can acquire data on the sky. So this is a picture of the camera. And you see each of these tiles here. So this is what contains the CCD chips at the focus of the telescope. And these are each of the CCD chips. There are 74 CCD chips, each 2,000 by 4,000 pixels, with a pixel scale of about 0.3 arc seconds per pixel. So you see these cameras are starting to get really impressive. I mean, the amount of CCDs and the amount of electronics behind, the wide field of view and so on is starting to be very impressive. And also what the control one needs on the telescope and the telescope optics now is very stringent. So this field of view corresponds to 2.2 square degrees. So in one observation, one can cover basically the cosmos field, the weight of the cosmos field. Of course, not at the depth and image quality of the Hubble Space Telescope, but in terms of area, we do one observation and that's it. We have 2 square degrees. And the goal of the survey is to eventually cover 5,000 square degrees in 5 bands, going again from the blue to the red, or near infrared almost, to this magnitude, and eventually measure the shape of 200 million galaxies. Okay. This was an image of a galaxy we got for the first light when it was turned on. The camera and everything worked quite well immediately, so we're very happy with that. Okay, so we started doing analysis. I'm saying we because in this case I'm involved in this experiment. At ETH, our group is involved. And then, so we started doing an analysis of the first data set. So it's called the SANS verification data. So this is a data set which is meant to check that the instrument is performing as instrument and survey are performing as we want for the weak lensing analysis. So it's only a very small fraction. So it's 170 square degrees out of eventually the 5,000 that we will cover. This is the pattern in the sky that we call the footprint of this SANS verification data. And what you show is a weak lensing mass map which I showed you the first day by Vinu Vikram and Chiwei Chang, who's at ETH. Chiwei is at ETH. And you see, so again, the dark, well not again, but the dark red is over densities, the blue is under densities, and you see all these interesting patterns. So again, one can make a map. But for cosmology, what we want is look at the correlation function. And here it is. So it's a little busy plot, so let me walk through it. So on the left is shown the correlation function in real space, and on the right is the correlation function in Fourier space. So this is the power spectrum, this is the correlation function. So what is shown on the top here, and by the way, you can look at all these papers which came out last year to describe all the analysis. So on the left here, this is this is 2 correlation functions for all the galaxies taken together without cutting in different redshift bins. This is not E and B, it's different combination of the correlation functions. So the second one is not meant to be consistent with 0 in that case. And you see very clear detection here all the way out to 100 arc minutes or more. Okay, and this is the same correlation functions, but this time by making different redshift bins. And in this case, 3 redshift bin, 1, 2, 3, and also so this is the autocorrelation of each of the bin on the diagonal, and on the off diagonal elements here, you see the cross correlation between the different redshift bins. And again, we have a detection of the weak lensing in all these bins. So it looks a bit flat because it's been multiplied by theta to make it flat, actually. So if you divide by theta, you will get the steep curve that we're used to. Okay, and then one can also do, as I said, a spherical analysis and measure the power spectrum in spherical harmonics. This was done using a software package called PulseSpice, which is used for the CMB. So now we're starting to be able to use CMB techniques on weak lensing data. The data is becoming large enough that one can start doing that, which is interesting. This was really pushing this CMB package to its limit because the area of the survey is still relatively small compared to CMB experiments. So all these edge effects, so in Fourier space, these edge effects are more of a problem. So this is a student at ETH called Andrina Nicola who did this particular analysis. You can also find it in that paper by Matt Becker et al. And she got this measurement of the weak lensing power spectrum. The top panels are the E modes and the bottom panels are the B modes. And the two different columns correspond to two different shear measurement pipelines. So in this analysis, we had two groups performing the shear measurement, so the step going from the images to the shears. As I told you, this is a critical step in the analysis. So the idea was to have two different groups doing it, and then we compare the results. And you see they agree relatively well. They have slightly different signal to noise because they make different cuts. One of them has more galaxies than one has less, and so on. But it's a pretty good agreement. The B modes are basically consistent with 0, and the results are compared to a theoretical model. In this case, the Planck, the prediction using the parameters, the central parameters for the determined by Planck. And again, the signal looks has the right behavior as a function of scale. And eventually, when we get more and more areas, we'll be able to do everything in Fourier space. So we'll continue probably to do in different two-point functions, but I think this one is particularly interesting. And then with these, we could constrain cosmological parameters. Okay, so now it's getting routine, sigma 8 and W, okay? So we've got sigma 8 omega m. Okay, very kind of a busy plot. But basically, these dark energy survey science verification data give us the purple constraints. Okay? And this can be compared to the CFHG lens constraints, which are the orange ones. All right? And you see that, first of all, the error bars of the DS science verification data are broader. The area is comparable, but it's shallower than the CFHG lens. And also the seeing is not as good. So the statistical errors are larger, so it's a bit larger. But if anything, it tends to push it up. The purple contours tend to be a little bit higher than the orange contours. And this can now be compared with Planck, which is here, the red. So as we saw before, the red is in some weak tension with the CFHG lens results. But it looks more consistent with the DES SV, so it tends to relieve the tension a little bit. But the error bars are still large, so it's not clear. I mean, one needs better data to be sure. And these are contours from various other probes. For instance, X-ray clusters. So these are clusters of galaxies are in gray. You see that they tend to be a bit on the low side. Planck lensing is the yellow, as we saw, also on the low side. And some measurement using galaxy clustering, and in particular redshift space distortions, are the green, which also tend to be on the low side. So that's meant to illustrate the mild tension between the large-scale structure probes and the CMB. But again, the errors are still quite big. And then one can try to constrain W. So this is a joint constraint between W and what we call S8, which is a combination of sigma 8 and omega, so sigma 8 times omega to some power, which is basically the power corresponds to this degeneracy, so it's the amplitude of these joint parameters on that plane. And then the DES science verification data give the purple, CFHG lens gives the orange. Again, the error bars are still quite large with strong degeneracies on W, so it's mostly upper limits. Planck is the red, which interestingly is actually centered on W less than -1 alone, when Planck alone is taken. And then when you combine everything, Planck plus all the other data sets, you get the gray contours, which are consistent -1, with an error of 10% or so. Okay. So it all works quite well, but one should keep an eye on this tension and see what happens in the future. And we're in the process, for instance, with DES of analyzing the first 2,000 square degrees of the survey. So 10 times the area of what I just showed you, a little bit shallower. But and the KIDS is also analyzing more data, and Subaru as well. So in the next year or so, there should be some very interesting results coming from weak lensing. Now, interestingly, as I alluded to before, one can also do lensing with the cosmic microwave background itself. So the cosmic microwave background also gets lensed. Everything gets lensed, okay? The cosmic microwave background also gets lensed. It's at a much higher redshift, so it gets lensed by more structures as the light travels, the photons travel from the CMB surface of last scattering to here. The cosmic microwave background is very smooth. So it's actually so the effect of lensing is of course more pronounced when the background source that you're looking at has very sharp features, like a galaxy, for instance, because then the gradients in the image is strong. So when you take derivatives and you distort it, you get more. It's easier to measure. On the other hand, the cosmic microwave background measurements are getting now extremely good, and so there have been a lot of improvements and impressive progress at measuring the weak lensing using the cosmic microwave background. So, for instance, this is a map of kappa done with the microwave background. Okay, so this is a mass map done with the cosmic microwave background. Still quite noisy. But one can measure the power spectrum now of kappa very well. So this is the lensing power spectrum done with the cosmic microwave background. The gray point are the Planck measurement, and the blue and the green, which is hard to see, I guess, are ground-based experiments. One is called SPT, and the other one is called ACT. So you see that it's getting quite good, the measurement. The different experiments agree quite well. They go out to also L of 1,000 or so, which are basically arc-minute scales. And this is a field which is also evolving very rapidly. Yep.
How do you separate out the different components that you will have in a CMB map and isolate only?
Very good, very good. So actually, what lensing does to the CMB, so the CMB temperature, is that, so you take the CMB temperature map that you would see without lensing, and then by lensing it, you kind of shuffle the pixels around a little bit, right? The lensing just shuffles them around. What this does is that it introduces non-Gaussianity. So the CMB is thought to be, the primordial fluctuations are thought to produce Gaussian temperature fluctuations, and the lensing produces a special kind non-Gaussianity, but it's a very special kind of non-Gaussianity. And you can write down an estimator by taking gradients of the lensing field, basically, that produces, of the shear, if you wish, of the lensing field that produces this special non-Gaussianity. And if you look at so you can also look at it, if you just take the power spectrum of the CMB without worrying about it, you can ask how the lensing affects it. So there's a small effect on the CMB power spectrum, but it's pretty small, but it's included in the fits. But by using this estimator, by using this gradient estimator and the various techniques to do this, you can actually separate it and get the lensing power spectrum or the lensing map on its own by looking at this as this very special non-Gaussian nature, which is imposed by the lensing. Yeah, that's a good question. Yeah. Okay, so what's very interesting is not only can we look at this, I mean, of course, one can just fit cosmological parameters, I mean, a model to this, get the cosmological parameter constraint. I'll show you some constraint before coming from this technique. But what's also very interesting is one can compare the CMB lensing to the lensing the lensing as measured from galaxies. And so people started doing this. So for instance, first, this is an intermediate step. This is a cross-correlation between the dark energy survey and, in this case, the SPT CMB lensing measurements. So here what is correlated, so this is the, what is correlated, this is the mass map from SPT. So this is the weak lensing mass map derived from SPT, but in the region of the DES survey. Okay, so this is the DES survey footprint, but this is actually the SPT map mass. And the first thing that the DES collaboration did is to compare this to the distribution of galaxies. So for the moment, not lensing, but galaxy density. Okay, so the visible light, if you wish. So this is, for instance, a map of the distribution of galaxies. And then one can cross-correlate the galaxy position, the galaxy density to the mass inferred from the lensing of the CMB. And the nice thing about it is that the galaxies can be split into redshift bins, right? And some of the lensing of the CMB is produced by structures which are traced by these galaxies, right? So the CMB is very far, redshift 1000, but some of the lensing come from low redshift, and it can be probed by galaxies, which in this case are between 0.2 and 1.2. So here is a plot that shows the cross-correlation between the galaxy density and the CMB lensing for galaxies in different redshift bins, going from about 1.2 to 0.2. So these are galaxies from 0.2 to 0.4, redshift 0.2 to 0.4, 0.4 to 0.6, and so on. So this is increasing in redshift. And you see, and the data points correspond to the measurement. And you see that there's a clear detection of this cross-correlation. So indeed, the CMB lensing is done by structures traced by the galaxies. And then we can basically get a tomographic information on the lensing of the CMB. Okay, and then the amplitude are fit by different models, and they look fine. They seem to be also a little bit on the low side, actually. It's not very significant, but it seems to be a little bit on the low side as well. And then one can do also a direct comparison between the weak lensing of the CMB with the weak lensing with the galaxies. So in this case, this is a correlation between the Planck and SPT CMB lensing and the DES, the DES weak lensing. Okay, so you take the DES weak lensing map, the CMB weak lensing map, and you do a cross-correlation power spectrum of the cross-correlation of the two signals, see whether the maps are correlated or not. Some of the structures doing the lensing of the DES galaxies should be the same as some of the structures doing the lensing of the cosmic microwave background. Okay? And this is a measurement of the modes. These are the E modes and the B modes. So the B modes are consistent with 0. The E modes is still quite noisy. But they tend to be significantly above 0. You can do an analysis and measure the amplitude, and you get a significant amplitude above 0. So there's a weak but detectable signal. And you can compare the amplitude of that signal with what you expect. And it tends to be, the error bars are still quite large, but again, it tends to be a little bit on the low side. But the errors are too big to say much. Okay, but this again will improve. The DS survey will have larger and larger areas. Some of the CMB experiments from the ground are also getting more and more data, and this analysis will be improved in the next few years. We should expect a lot of very interesting results there. Okay. Now, before I talk about the forecast for the future, let me say a few words about systematics, because in these measurements, now that the surveys are getting larger and larger, so what does it mean? The surveys are getting larger and larger. It means that the statistical error bar, the amount of information is increasing, so the statistical error bars are going to decrease. But that means that the level at which we need to control systematics is also increasing, right? Because our precision is higher, so we have more systematics to worry about. So let me talk about the main classes of systematics for weak lensing. Each of the different probes have their own set of systematics with different degrees of importance. So let me talk about the weak lensing. And systematics are really the muddy part of the measurements, right? I hope we're not bogged down like this. Or maybe this bull is enjoying itself, swimming in the mud, I don't know. So I guess it's both enjoyable and kind of difficult, and a lot of the work is done there. So that one can think about two classes of systematics. So first, there's the systematics associated with the measurement. All right. So there are different steps in the measurement. We have to correct for instrumental effects. There's probably errors. It could be problems in the analysis pipelines, all sorts of things, just purely from the measurement. And then the other one is it could be in the interpretation of the results. We could have the measurement can be fine, but we've ignored an astrophysical effect. And our interpretation when we go from the, let's say, the power spectrum, which could be fine because we've all our systematic for measurement under control. But when we go from the power spectrum to the cosmology, maybe there's some effect we didn't think about that can actually bias the cosmological constraints. All right? And then there are several of them. So for the measurement, one we've already discussed is the difficulty in measuring shapes. All right? So we can have systematic associated with the shape measurement. That's the step which goes from the images of galaxies to the shear estimation. Okay, we've talked about it a lot. I'm not going to come back to it. Another one has to do with our estimation of the redshift of the galaxies. Right? So to interpret the weak lensing power spectrum and to split the galaxies into different redshift bins, we need to have an estimation of the redshift distribution of the galaxies. And in practice, it turns out not to be trivial, so I'll talk about that. And then, for the astrophysics systematics, there's the effect of baryons, which have an effect on the power spectrum, the matter power spectrum, and therefore the weak lensing power spectrum on small scales that needs to be taken into account. And the other one has to do with intrinsic alignment of galaxies, which I'll talk about too. So let me talk about these three, as we've discussed this one again already. So first, photometric redshifts. So as I said, I hope you can see this, but what we need to do in a lensing analysis is we need to determine the redshift distribution of the galaxies we use for measuring the lensing. All right. So for instance, it could be the black line. So this is the number of galaxies per unit area, I guess, some units, as a function, or just the number of galaxies in a given survey, as a function of redshift. Okay, and you typically have a distribution like this. It peaks around typically 1 or so. Okay, so we need to know this. We don't need to know the redshift of in each individual galaxy very well. It doesn't matter. But what we need to know this distribution very well. Okay. Because that's what goes, this n of z is what goes into the calculation of the weak lensing power spectrum. And if this is wrong, then our interpretation of the weak lensing power spectrum will be biased. Another thing we need to do is we need also to make cuts in color or in redshift or something to produce our different redshift bins. So we need to take this sample, make some kind of cuts, and then be able to get some nice different subsamples at different redshift. And they need to be as well separated as possible. And once again, we need to know each of these well. Okay? That's when we do our tomographic analysis. Now, in principle, that would be very easy. You can say, okay, I'm going to take a spectrum of every galaxy, measure the redshift, and then I know it perfectly, right? The problem is that that's, in practice, both very hard and extremely expensive. Because if you can detect a galaxy using imaging, right, which has a very broad filter or response filter in wavelength. To make a spectra, you have to split the light into many, many, many wavelength channels. And of course, the signal to noise per wavelength channels is much lower, and therefore it takes much, much longer, much more observation to do it. And even if you use very big, the currently best telescopes that we have, the largest one, which are 8-meter class telescopes, either the VLT in Chile or Keck, also in Hawaii or others, then you can show that it's hopeless to try to get a redshift from every galaxy measured by surveys like we have now. They're way too faint and they're way too many. So that's hopeless. Okay, so what we do is we do a poor man's version of spectroscopy, which is called photometric redshifts. So we use the observations which are now in at least several bands, 4 or 5 bands, and from the observation, it gives us a spectrum, if you wish, with only 5 channels, a very poor spectrum. But it turns out that galaxy spectra are not too complicated, and by using this color information, we can get an estimation of the redshift. And this is called, this technique is called photometric redshift. And this is an example with the Sloan Digital Sky Survey. This is a plot of the true redshift, or the redshift estimated from spectroscopy, as a function of the redshift estimated using this photometric redshift technique. Okay, and you see this, the solid line is what would be the case if it was a perfect match. In practice, it's not perfect, but it's quite good. I mean, there's a scatter, but it's not a bad estimation. As I said, we don't care really about the scatter as long as we know it, because we don't need in lensing to know the redshift of every galaxy. What we need to know is the redshift distribution of the galaxies, but we need to know it very well. Okay, so there's a lot of work being done with this to try to calibrate the photometric redshift So in practice, we do take spectra, and we have subsamples of galaxies for which we have spectra. We can test our photometric redshift. We can test how well we reconstruct the redshift distribution. There are different software to do, or techniques to estimate the photometric redshifts. So there's a lot of work there which are improving the accuracy of the estimation of the redshift distribution. But that's a systematic that needs to be taken into account. And the uncertainty on the redshift distribution is folded into the cosmological analysis. So if at the end we have an uncertainty on this redshift distribution, then we take it into account. Okay. Another systematic is called intrinsic alignments. All right. So until now, we've assumed that in the absence of lensing, the galaxies are randomly oriented, right? And that any correlations in the shapes of the galaxies or any alignment or statistical alignment of the galaxies are produced by lensing, okay? And it turns out that's a very good approximation, but it's not quite right. Galaxies can also have some intrinsic alignments. So they can be intrinsically correlated. Their shape can be intrinsically correlated just because of astrophysics, okay? And that needs to be taken into account and corrected. Now, as you see, there's actually there's a reason why that can be done, and we can separate the two. And this is the following. So it's illustrated in this diagram. So let's consider now our weak lensing measurement. So we have the observer, galaxies here. So weak lensing, or the shear, what it does is that it correlates the shapes because there are some, dark matter concentration or something in the line of sight between the observer and the galaxies, and because of the light propagation perturbations, then the two galaxies appear a little bit correlated. So that's what we've been talking about until now. Okay. Now, what could also happen is that the two galaxies are intrinsically correlated. Okay. So there's an astrophysical effect. One galaxy is very close physically to the other. They feel each other's gravitational field, or it's during the structure formation process or something. And they can be correlated with each other intrinsically. So it's called intrinsic correlation. Another more subtle effect, highlighted by Hirata et al., is that what could happen is that you could have a galaxy which is distant, let's say this one, which is lensed by a dark matter concentration, as before. And then you could have a foreground galaxy which is not lensed by this because it's at the same redshift, at the same distance, but it could be correlated with the distribution of the dark matter. Let's say it feels the gravitational potential of the dark matter, okay? And therefore there will be because this is lensed by this dark matter fluctuation, and this feels the gravitational potential of the same dark matter structure, then one could also have a correlation. This we call a GI correlation. This we call an II correlation, intrinsic. This is GI, okay? Now, what allows us to correct this, and now this is done in weak lensing surveys, and it works quite well, but that needs to be improved for the next generation of measurements, is the fact that the redshift distribution, the redshift signature of these effects are completely different. Because the weak lensing is coherent when galaxies are very far away. So for instance, if you move this galaxy and put it here, it's still lensed by this dark matter structure. So this dark matter structure lens both this one and that one, and so you still get the lensing effect. On the other hand, here, if you move this galaxy here, they're very far physically away from each other, they're extremely far, and so they cannot feel each other. So they cannot be correlated, because in order for them to be correlated, they need to be physically close to each other. While for lensing, for them to have a weak lensing correlation, they need to be close to each other on the sky, but they can be very far away from each other. Okay? And there's a similar consideration for the GI term as well. So basically, by using the redshift information, one can separate the two. And that's why the weak lensing, the tomographic analysis is important, not only to get more cosmological information, but also to correct for this effect. So it's actually crucial. And there's a lot of work going on with this. And you can use surveys which are very shallow or surveys where the galaxies are very close to each other to measure the intrinsic. So if you want to measure the intrinsic alignment, you take galaxies which are very close together physically and you measure it carefully, and then you can learn about it, you can model it. Okay, another systematic effect, which is even more on the theoretical side, is called baryonic corrections. So if you look at the power spectrum of matter fluctuations, you can look at it for the dark matter only, but in reality, we also have a small fraction of baryons in the total matter budget. So the dark matter dominates, but we also have baryons. The baryons follow the dark matter quite closely on large scales, but as we discussed before, on small scales, the baryons tends to collapse more and form galaxies and clusters of galaxies and so on by falling to the bottom of the potential well produced by the dark matter. That means that on small scales, the power spectrum of the baryons is not equal to the power spectrum of the dark matter. On large scales, that's to a very good approximation of the case, but not on small scales. And the lensing is sensitive not only to the dark matter, but to any form of density perturbations. So it's also sensitive to the baryons, which are a small correction in terms of the total mass, the total density, but nevertheless needs to be taken into account in the future survey, especially when the precision increases. And what you see here is a plot by Zentner et al. That plotted the lensing power spectrum as a function of L. And this is the relative difference between what you get from having the baryons in and neglecting the baryons. And you see that on large scales, the effect is very small. But on large scales, you start getting deviations from the prediction from dark matter only. And in fact, these are different prescriptions. So the physics of baryons is complicated. So when people do simulations, they have different recipes for the physics of the baryons. And depending on the recipe people choose, then one gets different answer. Okay. So this needs to be modeled carefully. The good thing about baryons is that most of them are seen. So we know a lot about baryons, so we can model them, remove them. Something very powerful is to look also at the cross-correlation between galaxy position and shear, which also gives more information. There are various statistical techniques to try to remove the effect and so on. But this is something that that's a theoretical, systematic, if you wish, that needs to be taken into account in the even now, actually, especially when we want to access very small scales. Okay. Now to finish, I want to tell you about the future of all this, how well this will improve. And as I showed you before, there's a large number of surveys which are being planned and which will give us much more information, much better data in the future. And the ones that are more relevant for weak lensing are the one in the visible near infrared. And there's going to be a combination of imaging and spectroscopic surveys that will give us a lot of information. So let me focus on the ones, and as I said, in the radio, there's also some very interesting potential, which I won't have time to talk about, so very interesting. So let me focus on the ones which are relevant for weak lensing and for which weak lensing is one of the primary science drivers. So the ones that are online now and starting to give their results are the first two, and very soon the third one I expect. So one is the kids, I showed you the first results. The second one is dark energy survey, I showed you the first result. And Subaru, which we're expecting the results soon. What is shown here, which you probably can't read, that's the name of the survey, that's the diameter of the telescope. Okay? So you see kids is with a 2.6 meter, DES 4 meter, and Subaru is 8 meters, so much larger telescopes. This is the field of view of the camera, approximately. So this is about 1 square degree, 2 square degrees, actually a little bit more than 2. 2 square degrees, a little bit more than 2 here, I think 2. And this is the area of the survey which is expected to be carried out. So with kids, they'll get about 1,700 square degrees. There's 5,000. Subaru, I'm not quite sure actually what the final number will be. This is the dates. Actually, this is a bit out of date. This was I should have updated the table. They came online only in 2014, 13, 14, and so on. A little bit of delay. But they're starting to give their results, and in a couple of years they will finish all the observations and cover this area. So you see the area is growing very fast with different kind of size of telescopes. There's also another telescope called Pan-STAR, which is an interesting concept, which is an array of small telescopes, which has started some time back. The image quality of the first one was not as good as expected, so I think the lensing hasn't been done. But perhaps with the new elements that they put in, they'll get better results. So for the moment, only the first the first telescope was installed, and I think they're planning more. Then there's the most ambitious experiments. So this one is LSST. It's a ground-based experiment with an 8-meter telescope and a 7 square degree camera. So extremely powerful telescope, which will cover basically all the sky available in Chile where they will be, planned for 2020 also. This telescope also, what it will do, which is novel, which is very interesting, is it will take a large number, instead of taking a few very long exposures, is going to take a very large number of very small exposures, 15-second exposures, but hundreds of them. And this is interesting. This is called time domain because we're now going to have a time series of data. So each of them has a relatively small signal depth, even though LSST is such a big telescope, actually it goes quite deep, even one exposure. But the advantage is that we can use the time series to learn about the systematics of the point spread function and the shear measurement, and fold in all this new information into the analysis. Already with DES, we're going to get 10 exposures eventually, or between 8 and 10. And already with what we have now, we're starting to use these different exposures. But this will be a completely different regime. And then there are space-based experiments, which are also very ambitious. So Euclid is one I worked on with a 1.2 meter in space with about a square degree field of view, with both infrared and optical visible imaging. The idea is to cover 15,000 square degrees. The start date is around 2019 or so. And then an even larger telescope, WFIRST. This is still being defined as for more distant future, which is also being planned there, only in infrared, focusing on very high redshift, with also very good image quality with infrared detectors. So you see that, and this is coming in the next decade or so. You see that the prospect for improving the measurement is immense. Okay, so how much of a precision can we get with this? I'm almost done. So this is a calculation that we did, led by Adam Amara, who now at ETH, which shows the expected errors that we expect on different cosmological parameters for different surveys. Okay, we did this in the planning of Euclid to try to optimize the survey and see how well we can do. But it's applicable basically to the ones that will cover a very large fraction of the sky, 10 or 20,000 square degrees. At the time we were assuming 20,000 square degrees, but it doesn't make a very big difference. So what is shown here, so it's for different surveys, okay? And what is shown in each of the columns is the errors expected for the different cosmological parameters. And what we were considering here is an extended lambda CDM model where we have the lambda CDM parameters plus 2 parameters to describe the dark energy and its evolution. So it's W0, what we used to call, what's called W0 and WA, basically. Okay? So this is omega matter, omega lambda, omega baryon, sigma 8, the amplitude fluctuations, and the spectral index of primordial fluctuation and the Hubble parameter. And you see that a weak lensing survey that covers a very large part of the sky, about half of the available sky or so, will give extremely small errors on these parameters. At least the statistical errors, if we're only dominated by statistical errors and the systematics are subdominant, then one can hope to get these kind of levels. We can get sub% error on most of these parameters. And on the dark energy, we get particularly good errors because, of course, the survey was optimized for that. We get a few percent on W0 and less than 20% on WA. And this is alone, without any priors coming from anything, without CMB, with nothing. Okay? And these errors are comparable, actually, to the errors we get from the CMB. I mean, this is this kind of old numbers, but if you look at the errors on the CMB, the amplitude of these errors are comparable. The CMB does better in some parameters, the weak lensing survey do better in others. I mean, the weak lensing survey do particularly well on the dark energy. As I told you, it's as far as the statistical errors are concerned, is the probe that has the most potential for constraining dark energy. But what it means is that there's as much information in weak lensing surveys as there are in CMB experiments. Okay, it's as much information, and that's the regime we will be getting into. Now, of course, one can then combine the weak lensing with various other probes, and we can even combine these probes with the CMB together, and then we get like incredibly small errors, like tenths of percents or so on. Okay. Now, the goal is not necessarily to get to this level of errors. I mean, what's the point at beyond a certain point of reducing the errors? But what it means is that we can consider, we have so much information and so much precision, then we can start looking at extensions of the model in different sectors of the model and constrain them. So for instance, of course, the main one is dark energy, so we can constrain dark energy very well. We can constrain even more than 2 parameters. We can look at the evolution of W with a lot more parameters. We can consider dark energy perturbations, all sorts of things, and get very strong constraint on dark energy. We can also test the dark matter, cold dark matter paradigm. For instance, neutrinos, which are known to have a mass now, contributes a bit to the dark matter. We know they're subdominant, but nevertheless, turns out we can get very strong constraints. We can, on the mass of the neutrino, we can even detect the mass of the neutrinos and measure the mass of neutrinos with these surveys, which are actually competitive with neutrino experiments. We can also constrain the initial conditions. So here we assume that the primordial fluctuations are a power law, but they could be more complicated. We can constrain that. We can also test general relativity on large scales. So you can consider extensions of general relativity with more parameters and constrain them. It turns out we're very strong constraints on modified gravity as well. So but in the future, with weak lensing surveys and all the other probes and combination, we're going to get very, very strong tests of the lambda CDM model with extremely strong precision, but also we can look at various, try to look for new physics in any of these sectors. And I think if we find a deviation from lambda CDM in any sector, this will be extremely important. So the potentials are very high. Now, of course, for this, we need to control systematics. So we spend a lot of time trying to decide what is the level of systematics that we can tolerate. Okay, and for that this is again with Adam and Amara and others. So we quantify the amount of systematics. What we basically derive is the requirements on the systematic levels, which is needed in order for the systematic to be subdominant compared to the statistical errors, so that we can achieve the full potential of these surveys. And basically, this is the error on W as a function of survey area. This is the dashed line is the statistical error. So of course, as you increase the survey area, you get better and better precision on W. And the idea is to reach the percent level, you need several tens of thousands of square degrees with some assumptions. But if the systematics are at a too high of a level, the error will just plateau. Okay, and we could find a way of characterizing and putting the requirements on these errors. Now, in order to do this, there's still a lot of open problems. So for young people, there's a lot of things to be done. So I wanted to list them so that it may give you some ideas for projects or for future directions. First, on the measurement side, as I said, that's more on data analysis. If you like data analysis, there's some very interesting data analysis problems and a lot of advanced statistics, a lot of innovation there that can be done, both on the shape measurement and photometric redshifts. On the interpretation side, one needs to look at the astrophysical systematics. A very interesting thing I discussed, I think it was yesterday or the day before, was how one can fully characterize a non-Gaussian three-dimensional field in spherical geometry. So that's not been done. How do we tap all the information in this weak lensing survey? For the moment, all the errors I showed you here is only with the power spectrum. Okay, if you put in the non-Gaussian information, it will be even better, but we don't know how to characterize that well enough and do forecasts with them well enough. So that's an interesting field. And all of this needs to be done in quite a new regime in terms of data analysis compared to the CMB. The data volumes are much larger. So the resolution of a CMB experiment is an arc-minute or so. We have sub-arc-second resolution, so the amount of data is enormous. We need typically to combine data from different experiments. So it's actually very large heterogeneous data sets. So that puts constraint on the analysis. We cannot do very slow analysis. We do very efficient analysis with very high quality control. So that's more on the computer science side. So if you like computer science, there's a very interesting problems at the interface between computer science and astrophysics. And briefly to conclude, I just want to give you a little glimpse at one of the things we're pursuing at ETH, just to give you a feeling. I alluded to it before. What we're now studying doing a lot of work on is what we call forward modeling to control all the systematics. The idea is to model all the different steps in the measurement and in the data analysis. And in order to do this, for instance, just to give you an example, we developed some very fast software to generate images. So this is a DES image. This is one of our simulations. We can now generate these in very, very short time. So we can generate a full DES survey in 15 minutes or so on a very large number of processes, but nevertheless, a reasonable number. So it means that we can simulate the DES survey many, many, many times, do a lot of simulations, control systematics, calibrate our shear measurements. And we even have a scheme that we call Monte Carlo control loops, which allows us to loop through these simulations where we apply exactly the same analysis software to the data, to the simulations, and loop, test for systematics, test for the robustness, and so on. So we're working very hard now on this analysis to bring the level of systematics as low as we can. And we're applying it to various surveys, including the DS right now. So I think that's an interesting route as well. And the approximate Bayesian computation, which I was telling you about before, is one of the tools that we need for this analysis. And there again, there's some very interesting development there. So to conclude, gravitational lensing, I hope I convinced you, is a special probe in cosmology because it's purely gravitational. It's a direct probe of mass and has potentially very strong statistical power for dark energy and many of the other experiments. The way to see it, I think, is to see what we're doing, as I said before, is just like the CMB is mapping the background of the radiation temperature or polarization at the surface of last scattering. What we are probing here is the background of metric perturbations in the local universe in 3 dimensions. And that's a fundamental measurement which needs to be done and which has the potential of constraining our model, which is very strong. There are many wide field lensing surveys which are in the planning, so there's a lot of future to this. As I said, at least in the next decade or more, there will be an enormous amount of observational progress, and there are many open problems for young people. So I hope some of you can get interested in this subject. Thank you very much. I think I'm showing the SPT map. So just so you know, I've replaced it now in the slides, so now you've got the correct one. It has a slightly lower resolution, and this is, you can look at the papers, it's compared to the galaxy distribution and so on. So just for the record, I want to say that's the right one, and I've replaced it in the slides. Yep.
So now if you have some doubts or whatever,
questions?
last discussion.
Yep.
Actually, I have a pixelated image of a galaxy.
Right.
I have a point spread function.
Yes.
Now what I was trying to do is that I was taking just a computer generated small dot, and I want to encode the information from that point spread function into that dot, along with the theoretically calculated parameters from the model into that dot, and then can I go about pasting those dots on the pixelated image, and through that image I obtain a final corrected image of the galaxy. Is that possible?
So what do you mean by these dots?
It's just a computer generated small red color dot or black color
Okay,
dot.
you take a dot, and then
Yeah.
what do you want to do?
I want to paste it on the pixelated image. Like,
but the dot would correspond to what? It's like a photon from the galaxy, or what?
Nothing. That's just a computer. Like generally, you do it in graph digitizing.
Okay.
So just some.
But how do you use then the information from the point spread function?
I want to encode the point spread function's information into the dot. That particular dot will correspond to the point spread function. It will have the information from the point spread function and theoretically calculated parameters from the cosmological model. Let it be into that dot, and I go about pasting the dot on the pixelated image and docking.
Okay, so maybe we can discuss. I mean, I'm not sure. I mean, the PSF doesn't have any the point spread function doesn't have any cosmological information in it, right?
It just has the information about how the thing spread.
That's right. That's right. So I still don't. I'm not sure I understand what you want to do with. But how do you want to use the dots and the point spread function to get to the cosmology? I guess I remember.
See, I have three things. One is the pixelated image.
Fine. So you have an observed image of the galaxy.
Yeah.
Fine.
Other, I have a point spread function.
Okay.
That is also an image of the far star.
That's right.
Okay. And I have that is some dot that I am generating.
Fine.
Okay. I am putting down the information from the point spread function into the dot.
So what do you mean by that? What do you mean by putting information about the point spread function into the dot? I guess
the dimension of the dot corresponds to how the things spread about in that original galaxy, or the dot has
so you take the dot and you convolve it with the. I mean, you take the dot and you convolve it with the point spread function,
right?
And you pixelize that. Is that what you mean?
I also want to put in the cosmological parameters corresponding to the dimensions of the dot from the theoretically calculated method.
So so the dot has the dot presumably doesn't have a size, right?
I can take it to be some 1 micron or some size.
Okay, so where is the cosmological information there? Because I mean, either it's a dot or it's a point.
Getting it from theoretically calculated methods.
Fine. So you have your theoretical.
From the model I am calculating.
You have your cosmological model, and you can calculate all sorts of things.
Yeah, and
so
from
what?
The cosmological model theoretically, which I am calculating, that I am putting it into that also.
Putting into what? So what do you do with your cosmological model? What do you calculate?
All the parameters like the size and the mass density and other things.
Of the dot,
no,
of the PSF, of the galaxy. Well, I mean, your theoretical model is never going to tell you. I mean, you can. It's not going. It cannot tell you. You cannot predict the size of that galaxy, right? I mean, a theoretical model. Well, first of all, I mean, you can take your theoretical model and compute the statistics of structures. You can even make a realization with a simulation. But then, if you really, really work very, very hard, you can even try and simulate galaxies in that model. But you're never going to be able to say that galaxy here is going to have that size, right? You can look at the statistics of all galaxies, the distribution of the parameters of all galaxies, and try and fit it, and then see how this galaxy. You can look at the properties. For instance, you can have a model for the light profiles, and you can fit these models to your galaxy or something like this. But you cannot go from a cosmological model with 6 parameters to a prediction that there's going to be that galaxy looking like this here. I mean, maybe I don't quite understand what you're trying to do, but or should we discuss it afterwards? I don't know. I mean, I think it sounds like you have an idea, but I still can't quite understand what you're trying. So maybe if afterwards we can sit down, you can show me on the blackboard or something. Yeah.
Anything else? Anybody?
Yeah. So you actually showed the distribution of the photometric redshifts.
Yes.
And if you're looking at any survey, then the survey is looking at a certain redshift range.
Yes.
But the sensitivity at different redshifts is not the same.
Yes.
So therefore, the distribution that you're going to be getting is going to be both a function of how the galaxies are actually distributed and also how much sensitivity at different redshifts.
Yes. So
do you correct for those?
The distribution of what?
The number counts of the galaxies with.
Yes. So yes, you take all of that into account. Because it's true that if you look at the more distant ones, which tends to be fainter, then they're fainter, so the signal to noise of the image is lower, and so the information on the shear is lower, so the noise is higher, and that's also taken into account into the analysis, and that's true. So the more nearby ones are typically larger and brighter, The more faint ones are typically fainter and smaller, so they're harder. It's harder to measure the shape. On the other hand, the faint ones have more lensing signal because the shear power spectrum is larger when the galaxies are further away. So there's kind of a competition between these two effects, and there's an optimal place to measure it. Now, of course, we always try, in principle, we'd like to go as faint and small as we can and high redshift. But of course, there's a limit, and you have to stop because below a certain limit, there's not enough information to measure the shapes. And that's also taken into account, definitely.